second. Let me turn on my camera.
Oh, okay, great. I guess 1 year ago at similar time for the STW 2021, I'm honored to introduce Professor Una Mutlu. And now in STW 2022, I'm honored again to introduce Professor Una Mutlu. So again, thanks Professor Mutlu for, I would say, attending the STW. And I mean, for those who are working on cybersecurity area, you must know him, but I still would like to read one part of the bio. Una Mutlu is a professor of computer science at ETH Zurich. He's also a faculty member at Carnegie Mellon University. His current broader research interests are in computer architecture, systems, hardware security, and bioinformatics. A variety of techniques he has invented over the years have influenced industry and has been employed in commercial microprocessors and memory storage systems. He obtained his PhD and master in ECE from the University of Texas at Austin, and the bachelor degree in computer engineering and psychology from University of Michigan, Ann Arbor. He received numerous awards. I don't want to repeat all of them because then I would take too long time to do that. But just want to mention that he is an ACM fellow and IEEE fellow and an elected member of the Academy of Europe. His talk title is The Story of RowHammer. Professor Mutlu, podium is yours.
Okay, thank you very much, Lynn, for the introduction. Can you hear me fine?
Yes, we can hear you. I guess you needed to share your screen.
Okay, I think my headphones are connected now. Let me share my screen over here. Okay, I assume you can see the slides as well.
Yes.
Okay, great. So I'll get started. Thank you very much for inviting me to give a talk. I could talk about a bunch of security projects that are ongoing in the group, but I decided to talk a little bit more about RowHammer because I think, first of all, this is a fun topic, and there's a lot going on right now on RowHammer related issues. And I believe there will be more going into the future, as was mentioned by Rainer in the previous talk also. Maybe we'll get to that toward the end of this talk. I have a lot of slides over here. I'm going to skip some of them because this talk is relatively short, but these slides will be made available. They're pointers for future, for past papers and more depth if you want to go more into the topic. When I talk about RowHammer, I start with this bridge. This bridge that doesn't exist anymore because a bit flip happened to it in 1940, 6 months after it was built. And clearly it posed a safety, security, and reliability problem. And I think there are other examples like bit flips in real life. This example, people are building an important city and a bit flip happens and they will not be happy very quickly. I think in real life, we face these challenges where reliability of structures immediately affect our safety and security. And I think that is true in memory systems, as we will see in RowHammer. And that's going to be increasingly true in the systems that we build that are going to be operating in the field, making decisions for us, and that we're going to push to the limits. So hardware security is going to be increasingly important, especially from the perspective of reliability. I like using this example also. This is a joke, clearly, Mr. Bean driving a car or self-driving a car. And if you think about a bit flip happening in this self-driving car that's not controllable, then we have a problem in our future. And in the future, we're going to have a lot of systems that are making decisions for us, life-critical decisions for us, safety-critical decisions for us. This is true for existing technologies as well as emerging technologies, like emerging memories, for example, and emerging computing paradigms like memory-centric computing and processing in memory. In fact, more so in emerging computing paradigms probably. So what is RowHammer? RowHammer is the fact that you can predictably induce bit flips in commodity DRAM chips. And at the time we reported the problem for the first time, we found out that more than 80% of the tested DRAM chips are vulnerable to this. And this is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If you know of some other mechanisms, please let me know. I think RowHammer is a great example of this. And as a result, people are writing articles that look like this, which I very much like. Forget software. Now hackers are exploiting physics. Clearly, security community has been focused on software for such a long time. I believe those are interesting issues, but the root of trust is really at the hardware level, as we know very well, because all of that, those software mechanisms can be hacked unless you have a very strong root of trust at the hardware level. And I think RowHammer breaks that root of trust right away. That's why it's very interesting. So I'll give you some perspective very quickly. Basically, we've been having a lot of technology scaling issues in memory, and we've been writing papers about it. I'm not going to bore you with the details of these papers, but we're going to focus on DRAM, dynamic random access memory, although RowHammer, in my opinion, disturbance errors are more general than DRAM. But DRAM is very, very interesting because all of our main memory systems are built with DRAM. And for DRAM to increase in capacity, you need to reduce the size of the capacitor, which stores charge, which stores data essentially, and you need to reduce the size of the access transistor. And as you reduce the size of both of these things, as well as peripheral structures, it becomes difficult to keep this reliable. There's a lot of noise effects that come into play. Retention time becomes a problem, and I will mention that in a little bit. Disturbance becomes a bigger problem. And we've been doing a lot of experiments in this field. This is data that we gathered together with Facebook over the course of a couple of years in 2013. It was reported in DSN 2015. Basically, we looked at the correlation between the DRAM chip density employed in production data center servers at Facebook, all of their servers, and the server failure rate. And you get a significantly strong correlation, which means that if you employ a denser DRAM chip in your data center, you're more prone to errors. And these are real errors that you experience in the field. Why? Because cells are smaller in this chip. They're more vulnerable to noise. Cells are close to each other. They're more vulnerable to noise. As a result, you get more errors. And this trend is still continuing. We are having less and less reliable chips going into the future. And if you're interested, we've been doing a lot of work in this area as well. So we wanted to understand some of these reliability issues. So we built a lot of FPGA-based testing infrastructures. The first one is shown at the bottom right over here. And we wanted to basically look at what are the reliability issues lurking in memory that can threaten dependability, robustness, as well as safety and security. And this is actually where we did a lot of the RowHammer experiments. We scaled up the system, and we released this FPGA-based infrastructure as open source software. A lot of people actually are using it. A lot of people interested in this topic, and they built. They basically came up with a lot of interesting insights as well. I might mention them. And if people are interested in using it, we release this infrastructure. We're going to release a new version of it that is capable of testing DDR4 chips within the next week or the week after. So stay tuned for this. So the main reason why we built this infrastructure was to understand the technology scaling issues of DRAM. And one major technology scaling issue of DRAM is retention failures. So DRAM cells leak charge over time. As a result, they lose data. So the cells need to be refreshed periodically. And every cell needs to be refreshed every 64 milliseconds at the time. Today, we're actually reducing that. In newer DRAM standards, it's 32 milliseconds. So refresh is becoming a bigger problem. We wanted to understand if we can get rid of that reliability problem somehow in an intelligent manner. I'm not going to go into the details, but with this testing infrastructure, you could test the retention time of DRAM cells, and you could find out that an overwhelming majority of DRAM cells don't need to be refreshed as frequently as we refresh them today. Basically, you can cut the refresh rate by 75%, which increases the energy efficiency and performance of computers. But of course, it's not easy to do. There are many, many interesting challenges over here that I'm not going to go into in this talk, but I just want to give you the idea of why we built this infrastructure. And these are some papers that we wrote about reducing the refresh overhead in existing DRAM chips. We're going to get back to this refresh because refresh is actually very interesting. It is a very interesting interaction with RowHammer. And these are some papers that I'm not going to cover. There are a lot of interesting insights that you can develop once you have an infrastructure like this and try to understand what's going on inside the DRAM chips. And this is one of the latest papers. In this latest paper, basically, we try to identify uncorrectable errors in memory chips that use error correcting codes. Okay, so that was refresh. We'll get back to this. And that is enabled by this infrastructure. While we were doing these studies, we were also thinking about what else can we do with this infrastructure that is very interesting. And we also had a flash memory infrastructure where we were seeing a lot of read disturbance errors in flash memory, in SSDs, essentially, NAND flash memory. And we asked the question, do we actually have disturbance errors in DRAM as well? And we tested the DRAM chips, and we found out that that was the case. Basically, one can predictably induce errors in most DRAM memory chips, and that's what RowHammer is about. I've already given you this. So what's RowHammer as it's manifested in DRAM chips? Essentially, when you access DRAM chips, you have a bunch of rows. And if you want to access one row, you need to activate that row, apply high voltage to that row. If you want to access some other, you need to deactivate that row and activate some other row. You need to apply low voltage to this particular row that you activated earlier. This is the second, the first command is called an activate. The second command is called a precharge in DRAM. Now, if you keep doing this repeatedly, activate, precharge, activate, precharge, activate, precharge, activate, precharge, high voltage, low voltage, high voltage, low voltage, it turns out that some cells that are vulnerable in physically adjacent rows in the same bank get bit flips. Their value goes from 1 to 0 or 0 to 1. And this clearly should not happen because we're just reading a row. We should not be disturbing anything in the, let alone other rows. And the stuff, the data in other rows may belong to some other application, may belong to the operating system, or may belong to your own application that you don't clearly want to corrupt. Right? This is simple data corruption in memory. And we call this the hammered row, and we call this the victim rows. And we showed that more than 80% of the chips that were manufactured by the three major manufacturers, there are only three major manufacturers in the world, are vulnerable to this problem. And this is a technology scaling problem because the chips that we tested before 2000, that were manufactured before 2009, were not vulnerable to this problem because you could not cause enough activates to DRAM within a refresh interval that would induce a bit flip. Later chips were all vulnerable. 2012 and 2014 were all vulnerable because cells became smaller enough, and the number of activates you needed to cause a bit flip became low enough that you could fit enough activates within a refresh interval. And that's the idea, basically. So why is this happening? Basically, DRAM cells are too close to each other. They're not electrically isolated from each other. Access to one cell affects the value in read-by cells due to electrical interference between the cells as well as wires used for accessing the cells. This is also called cell-to-cell coupling interference. Now, I'm not going to go into the device level issues. There are a lot of interesting things that are to be examined in the device level, and we covered that in our papers as well. But at a high level, the abstraction is when we activate or apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if you do this hammering enough times, charge in such cells get drained. And if you do it enough times before the cells get refreshed, you're able to cause data corruption. That's the idea. And it turns out this has enormous implications at the upper layers of the transformation hierarchy. Clearly, it's a reliability problem because this could cause data corruption. But this data corruption can be exploited as a security problem as well. And that's what has happened since we introduced the work. So this is how a user level program can introduce this data corruption using RowHammer. Basically, it's a very simple program. You could actually make it even nicer, let's say. It selects addresses X and Y such that it avoids caches to those X and Y, and then it avoids row hits to X by reading row Y. So basically what it does is it hammers these two rows, and if the DRAM cells are vulnerable, you get bit flips. Now you could choose addresses X and Y such that you sandwich one row in between them, and that actually increases the amount of bit flips you can get and the number of activates you need to do to actually get to the first bit flip, because it really increases the electrical interference in that particular victim row that you're sandwiching between X and Y. So there are a lot of tricks you can play in terms of choosing addresses X and Y, basically. And we showed when we first wrote the paper that real chips are vulnerable, as you can see over here. There's nothing special about Intel and AMD. All chips that have a good enough memory controller that obeys the standards can actually cause bit flips in chips that are vulnerable. And when we wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I think this is very fundamental. This is really the root of security, isolation in hardware. But RowHammer breaks this isolation property. And we said that one can cause data corruption, but one can also hijack your computer. Someone can basically relatively easily build a security attack that can take over your system. And while we were looking into that, the Google Project Zero folks showed essentially that. I refer you to their Black Hat presentation as well as blog post. This is the direct copy and paste from their blog post. They basically repeated the problem. They were able to build two working privilege escalation exploits. And one of them was very interesting. As a user level process, this process was able to induce RowHammer bit flips in its own page table entries that pointed to its own page table. And as a result, by flipping the right bits with some good security engineering, it was able to gain read and write access to its own page table And once a user level process gains read and write access to its own page table, that means that all bets are off. It can gain any type of access to the system. And that's what made this, let's say, famous as the DRAM RowHammer vulnerability. And people started drawing pictures that look like this. None of these are my pictures. These are actually nice pictures, I think. And one famous hacker on the internet said RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. And I like this analogy also. So later, there's a lot of work in the security community that built a lot of attacks. I'm not going to go into the details of all of them. You can read our retrospective paper that I'm going to mention later that covers a lot of this work, but not all of it, as we will see. These folks show that you could gain unrestricted access to systems of website visitors by inducing these errors through JavaScript. These folks show that you could gain access to cell phones that run the Android operating system. It's a beautiful attack, actually. I won't have time to cover it. These folks show that you could exploit these attacks using GPUs. These folks show that you could do these attacks through the remote direct memory access engine on a remote computer. These folks showed essentially the same thing concurrently. And these folks show that even if you are not able to gain root privileges on a system, you could break confidentiality by using RowHammer as a side channel to read the data that you're not supposed to read. So this is not just an integrity problem, but it's also a confidentiality problem, as we see. And more recently, there are works in neural networks showing that you could induce RowHammer bit flips in neural networks that are otherwise quite accurate in terms of inference, and your inference accuracy tanks to unacceptable, completely unacceptable levels because someone is inducing these RowHammer bit flips. And there are more works that I'm not going to talk about. So if you want to get a good overview of what has happened in RowHammer, especially until 2009, we were invited to write this retrospective paper, which covers issues all the way from devices to system security and operating systems, etc., including architecture, of course, and circuits. And it covers a lot of the works. What it doesn't cover is what has happened in 2020 and 2022, which I'm going to focus on after I spend some time on understanding RowHammer. So our initial paper was written to understand RowHammer. That's the paper. I'm going to give you some results. We tested a lot of chips, as you can see over here. And we basically saw a lot of interesting phenomena. So one phenomenon is at the memory controller level, the addresses of the aggressor rows and the victim rows are mostly adjacent, but there are some addresses that are not physically adjacent, not logically adjacent from the memory controller's perspective. Now, this is because memory controller doesn't have the exact physical locations of the rows. This is very interesting because internally DRAM remaps addresses. That means that memory controller level solutions cannot be perfect because they do not have enough knowledge about the physical layout of the rows in DRAM. So this may be interesting for solutions as we will discuss. Access interval. So one way of reducing the RowHammer vulnerability is activating rows less frequently. The DRAM standard at the time says you could activate every 55 nanoseconds, but if you actually activate less frequently, you get rid of the errors, as you can see. Y-axis, the error rate. So, but to be able to do this, you need to activate a lot less, which means that you reduce your performance significantly. Okay, this may be a solution, but it's not a great solution if you actually apply it to all accesses. Refresh interval. Every 64 milliseconds, everything was refreshed at the time we tested the DRAM chips. If you actually increase that refresh interval, refresh much more frequently, you can reduce the error rate due to RowHammer because you're giving less time for an attacker to activate rows. But in order to be able to get rid of every single RowHammer bit flip, you need to increase the refresh rate by 7x, which is not good, clearly. Okay, so clearly this could be a solution, but it's not a good solution. A data pattern is also interesting. Basically, data patterns that induce a lot more electrical interference, charge coupling, lead to a lot more errors, as you can see over here. Okay, we have a lot more results in our paper. Basically, ECC doesn't work. Double-sided hammering is good. Errors are repeatable, which makes the security problem. I'm not going to go over this. If you're interested, you can read the paper for more detail. And we have a lot more analyses as we will discuss. So more recently, we've shown that RowHammer is getting much worse. And we've been looking at new RowHammer dimensions like voltage, temperature, etc. I'm going to talk about that very briefly in the remaining time. But before we go into it, let's talk about RowHammer solutions a little bit. Clearly, we need to have two different kinds of solutions. One is immediate, because there are some DRAM chips that are vulnerable in the field. There are limited possibilities we can employ over here. And the other is longer term. How do we longer term protect future DRAM chips as well as other chips in the field? We propose both types of solutions in our original paper. I'm going to mention one of them, Para, and then we're going to talk about solutions toward the end of this talk as well. So clearly, these are some of the solutions, but they're not necessarily good. the solution that was immediately employed in the field was increasing the refresh rates, which is not a good solution, as we discussed, right? Because you need to increase the refresh rate a lot. But this is a security release from Apple. And Apple was nice enough to cite our paper in their security release, as you can see over here. They basically said to fix RowHammer, we increase the memory refresh rates. They didn't say by how much. They probably have increased by 2x. That's not good for performance as well as energy and quality of service. And that reduces the vulnerability of RowHammer, but it doesn't get rid of the vulnerability completely. So as I said, if you want to get rid of the vulnerability completely in the chips that we tested at the time, you need to increase the refresh rate by 7x. Today, it's much worse. That 7x has gone to 16x or so if you want to get rid of every single bit flip, because chips have become much more vulnerable to RowHammer. So this is not going to be a good solution. We need to find better solutions, especially with processing in memory technologies that are going to be out there accessing the rows much more frequently, potentially. Okay, our solution at the time was probabilistic. Very quickly, to give you the key idea, after closing a row, memory controller activates or refreshes one of the neighbor rows or both of the neighbor rows with a low probability. And if you're paranoid, you can increase this probability, as you can see. And this gives you a great reliability guarantee that's much better than anything else in the system. And you could strengthen that guarantee by increasing the probability of activation. And as we showed that this is stateless, and it's quite good in terms of performance and power. But as I will show you later, this doesn't scale very well to the RowHammer vulnerability that we have in today's DRAM chips. This is a good starting point, but this is not the full solution. And you could actually implement the DRAM chip and the memory controller. And Intel actually implemented a version of this at its memory controllers. And you can see that in their BIOS, it's a BIOS configurable. I'm not going to go into the details of this much. And if you're interested, we have the original solutions in our paper, but I'm going to talk about this more. But I believe the key takeaway here is that we need some intelligence in the main memory to handle issues like this. Either it has to be in the memory controller or it has to be in the DRAM chip. Probably in both, in my opinion, going forward, with some system level implications as well, because DRAM chip itself is not enough, as we will see. So we need some more intelligence, basically. And we have intelligent SSD controllers. We have done a lot of work in this area. I believe DRAM should look more like SSDs going into the future, incorporating mechanisms for error control that SSDs have a lot in the field today. And this is one paper that we wrote based on our SSD work. If you're interested, you can take a look at it. Okay, so there's a lot more I can talk about, but I will refer you to the retrospective paper that talks about what has happened until 2019 or so. Now I'm going to focus a little bit more on what has happened since 2019. Basically, we hope that RowHammer would be a solved problem by now, but what has happened is quite interesting. Basically, things are not getting better. RowHammer is really a technology scaling problem, so it's going to be very difficult to solve completely in the field, and devices are going to be much more vulnerable. And that's what we wanted to study, basically. In 2020, we published this ISCA paper where we revisited RowHammer, and we wanted to do a scaling study. We wanted to understand across many generations of DRAM chips, many standards, are the new chips better or worse at the device level if you turn off all the RowHammer protections, basically. And we found out that they're getting much worse. Basically, you get more bit flips due to RowHammer, and bit flips are happening earlier after smaller number of activations compared to about 10 years ago, let's say. Essentially, there are new chips whose weakest cells fare only after 4,800 hammers, double-sided. So if you multiply it by 2, 9,600. And chips of newer DRAM technology nodes exhibit RowHammer bit flips in more rows and farther away from the victim row. And what is worse is existing mitigation mechanisms are not scalable. They're not effective at future technology nodes. They either do not work at all, they're not designed for very small RowHammer thresholds, or they impose very high performance and energy overheads. So I will not go into a whole lot of detail since we don't have a lot of time, but we built a lot of infrastructure for this purpose. And we actually tested more than 1,500 DRAM chips across many generations over here, as you can see. Again, you can read the paper for more detail, but a key conclusion is that going from old to new DDR4 technology, you see more RowHammer bit flips, as well as bit flips happen earlier at smaller number of activations. These are called hammer counts. So basically, technology is not on our side in this problem. Our technology, we want to push the technology generations going into the future with smaller and smaller DRAM cells and newer technologies. Unfortunately, as you make those technologies smaller and smaller, the problem becomes worse. And this is another piece of data. I'm not going to go over this. You can read the paper for more detail. Okay, so that's interesting. This is device level, not good, basically. At the system level, manufacturers were implementing solutions. And one interesting thing happened. Basically, manufacturers said, okay, we have now RowHammer free chips. 2 manufacturers at least publicly came through and said this. They didn't say how. So this was clearly challenging for researchers, right? Basically, the manufacturers claim that they have RowHammer free chips. Is this really true? And we took on the challenge. Basically, we basically showed that this is not true. The manufacturers implement what is called target row refresh, and internally DRAM cells get refreshed with some algorithm that is employed proprietarily inside the DRAM chips to protect against RowHammer. And we basically showed that they cannot protect against RowHammer. We introduced an attack that's called the many-sided RowHammer attack. And the idea is to hammer as many rows as possible to bypass the internal mitigations. Internal mitigations usually work by detecting how many accesses do you do to some number of rows, but they do not have limited, they have a limited set of tables to keep track of how many activations you do to each row. And if you overflow these proprietary tables that are not exposed to anyone, you could actually induce these bit flips. So you're back to square one, essentially. To be able to do that, we partially reverse engineer the internal mechanisms that are employed in the DRAM chips. And we basically provide an automatic tool that can effectively induce these bit flips despite the mitigations. So these are some example hammering patterns. So this is double-sided RowHammer plus an assist row over here. This is a four-sided RowHammer attack over here. Red ones are the ones that we hammer, as you can see. And you can see that this is data from real modules. In some cases, you need to go up to 9-sided RowHammer so that you can overflow the tables internally. And this is a table. We showed that basically a number of modules are vulnerable. In some cases, the best pattern is 19-sided over here. So basically, you can circumvent the protections, and mobile systems are vulnerable. These are real mobile systems where we induced real bit flips and took over the system. And the attack times are relatively fast. For example, the page table entry attack is only 2.3 seconds in this particular module in a real system. Okay, so that's TRRespass basically. It turns out the existing solutions are vulnerable, even though they're advertised as secure. And our tool was not even exhaustive. There's a lot of room for uncovering more vulnerable chips and phones. And we actually will show that in a little bit very quickly. So what TRRespass shows was that RowHammer is still an open problem, and security by obscurity is likely not a good solution. So we need to be a lot more open in our solutions to this. I strongly believe this, actually. So, okay. So we also asked the question, can we somehow guarantee that a chip is RowHammer free by doing enough testing in the field? And I'm not going to go into the detail over here. We wrote a paper with Microsoft Research on this topic. Unfortunately, the answer is no. It's very difficult to guarantee a chip is RowHammer free. If somehow we can figure this out, that'd be good, but I don't believe that there is an easy solution to this. We also wanted to uncover the existing mechanisms completely. We wanted to understand what's going on inside the DRAM chip. So we developed this methodology that basically shows that industry adapted solutions can be almost completely reverse engineered. And that's the idea of uncovering TRR. This is a new methodology that leverages data retention failures to uncover the inner workings of TRR. So the basic idea is very simple. And we build on our expertise in data retention over here. You figure out which rows can retain data for how long in DRAM. And you induce a RowHammer attack on those rows. And if you select the rows carefully, you would induce a RowHammer attack on rows that would otherwise not be able to retain data long enough. If it turns out these rows get refreshed, then you will figure out that it gets refreshed by the internal mechanism that's employed by the DRAM manufacturer. So basically, we use the fact that a rows get refreshed as a side channel that an internal target row refresh is happening to protect that row against RowHammer internally. That's the idea, basically. So once you figure that out, you can figure out what's internally implemented in the DRAM chips, and you can craft new RowHammer access patterns. And we basically show that with our new RowHammer access patterns, all modules we test are vulnerable. More than 99% of rows in a DRAM back experience at least one RowHammer bit flip, and ECC is completely ineffective, basically. So basically, you can reverse engineer essentially everything. I'm not going to go into the details. It's fascinating. We actually released the source code of it very recently, and you can take a look. But you can see, for example, what we've discovered based on different manufacturers. Different manufacturers implement different strategies for RowHammer protection over here. And you can see there are a lot of interesting design options over here. And essentially, all chips we test are vulnerable to different degrees. If we actually put more effort, these chips that look like that are less vulnerable are actually also vulnerable, we believe. Even more vulnerable, as we believe. Okay, there's a lot more in the paper that I'm not going to talk about at this point. But basically, this sort of studies showed us that reinforced our belief that the security solution should not be through obscurity. We need to have a much more open solution. And anything that can be reverse engineered can be reverse engineered or will be reverse engineered by someone. Okay, so we actually analyzed RowHammer in many different ways. Since we don't have a lot of time, I'm not going to go into the details of it, but RowHammer has interesting interaction with temperature, aggressor row activation time, and there's an interesting physical spatial variation on this. And you can exploit all of these either to build better attacks or better defenses. Let me give you some examples. So we actually, these studies take a very long amount of time. It's not easy to do these studies. So we built a lot of infrastructure for this also. And we tested a smaller number of chips because they take a long time. It turns out RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor is active for a longer time. And there's a good spatial variation. Some certain physical regions of the DRAM module that's under attack is a lot more vulnerable. I'm going to talk about the last one because we don't have a lot of time. Let me talk about that last one over here. So spatial variation analysis. Some rows are a lot more vulnerable. You can see these rows over here are a lot more vulnerable than some other rows in manufacturers see across different modules. There's a huge variation in vulnerability. Similarly, some columns are a lot more vulnerable to RowHammer than some other columns. So if you actually figure this out as an attacker, and you could potentially do this over time as a silent attacker, let's say, then you can actually build an attack that's much better. Or from the defender's perspective, you can build a defense that's much better because it turns out a very small fraction of the rows, like 10%, are much more vulnerable to RowHammer compared to a majority of the rows. And if you actually realize that somehow, and if you're able to build defenses that can take advantage of this, you can make the defense mechanisms a lot more efficient compared to the past. I'm not going to talk about the temperature because we don't have time. So there's a lot more analyses in this paper. We still are understanding RowHammer, and there are many, many dimensions to it. The fact that I think the importance of doing these studies is as follows. If we don't understand RowHammer enough, then we'll build defenses against it based on our current understanding. And those defenses may not be foolproof because they may be assuming some thresholds that may be violated at certain temperatures, for example, or for certain rows. That's why we really need to understand RowHammer much better so that we can have a foolproof defense. Okay, there's more RowHammer analysis. I will not talk about the word line voltage analysis that appeared in DSN. This year, we built another infrastructure to make sure that these studies are done very well. It turns out you can reduce the RowHammer vulnerability by reducing the voltage that's applied to the word line, but this comes at a trade-off. That trade-off is favorable, but this doesn't solve the problem overall. Let me talk about new RowHammer solutions. So we introduced a BlockHammer solution in 2021, which I believe is actually a step in the right direction going into the future. This work was recently awarded an honorable mention by the Intel Hardware Security Academic Awards. Basically, we covered the space for RowHammer solution approaches. I believe there are two major approaches like reactive refresh and proactive throttling. These are two major prominent approaches that are going to be interesting going into the future. We can discuss that if we have time. But all of the approaches will have issues. It will be part of a trade-off space in terms of cost, power, performance, and complexity. So our goal with BlockHammer was to solve two major challenges. One is scalability. RowHammer vulnerability is getting worse. Can we actually tolerate RowHammer at very low thresholds, like 1K, for example? Or can we keep it compatible with commod DRAM chips? We don't want any changes to the commod DRAM chips. We just want changes to the memory controller. Can we do this? And that's the idea over here. The key idea is, at the memory controller, detect which rows can be potentially causing RowHammer bit flips and selectively throttle memory accesses to those rows. So I will not go into the details of the mechanism, but we have area efficient bloom filters to detect a RowHammer attack. And we can selectively throttle accesses from within the memory controller such that bit flips do not occur. And we can also optionally inform the system software about the attack so that system software can do something about it. And the key is this is compatible with commod DRAM chips. You don't need any information from the DRAM chip. It's fully secure because we're not based on refreshing. We don't rely on any internal information about the physical layout of rows. We're just throttling accesses at the memory controller. So it's perfectly secure compared to reactive refresh-based approaches. Okay, since we don't have a lot of time, I will not go into a lot of detail. I will give you some results. Results are actually quite good. Its performance and energy overheads are negligible. It's as good as other mechanisms that are less scalable, let's say. And whenever there's an attack, it actually is much better than other mechanisms. It can throttle the attack and make the system run like as if there is no attack. That's the good part. Other mechanisms actually suffer and turn the system. A RowHammer attack becomes a performance hog in other mechanisms. Okay, there's some slides over here. If you're interested, we've open sourced this, as well as 6 state-of-the-art mechanisms, and we will keep updating this repository. This is the repository that contains, as far as I know, all the most major RowHammer solutions to date. So this is an example of what I said earlier. Main memory needs intelligent controllers for security, safety, reliability, and scaling. And I strongly believe this. So there is more RowHammer in the last 3 years that I will not talk about. You can find some references to these works. So some conferences have actually sessions on RowHammer, as you can see over here. And there keeps happening interesting RowHammer papers. For example, this was in HotOS. And there are interesting attack papers also, as you can see over here. And this is an interesting session in IEEE Symposium on Security and Privacy that has both attack papers as well as defense papers. And there's more papers that are happening. I will not talk about it, as I said. This was at Usenix Security more recently. CCS has some interesting papers. Upcoming Micro has multiple papers. And it has one of our papers also that I will not talk about. I believe the solution needs to be more transparency in the DRAM system, which I'm happy to discuss if you have time. And we have some interesting solutions that actually push the solution to the DRAM chips. I will briefly talk about this because I think this is going to be a lot more important going into the future. We call it self-managing DRAM. And the idea is to give some breathing room to the DRAM such that it can do these in-DRAM maintenance operations. RowHammer is an example of this. So the DRAM can say, I don't receive your activate memory controller. I'm doing some maintenance operations. I'm fixing RowHammer, for example. So we basically add an NACT pin to the DRAM chip such that the DRAM chip can say this. And DRAM chip can say this until it finishes the maintenance operation. The maintenance operation can be completely implemented within a DRAM chip. And DRAM manufacturers know the characteristics of these maintenance operations more than anything else, arguably. So with this mechanism, we showed that you can implement DRAM refresh, RowHammer protection, and memory scrubbing. And as a result, you can gain a lot of speed up and lower DRAM energy with these mechanisms implemented compared to without these mechanisms implemented. And if you're interested in this, my PhD student Hassan delivered a talk on self-managing DRAM that you can find online. And there's much more in our preprint as well. So clearly there's more coming in 2023, but I'm happy to talk about that separately. Okay, I'm going to skip these slides. Clearly there's a lot more in the future, but we don't have a lot of time. I think other technologies are also similarly vulnerable, but we need to really understand what's going on. I have beautiful examples of bridges over here also. So bridges are going to fail. Computing systems are also going to fail. These bit flips are going to happen. The question is, what do we do about them? The good thing about computing systems is they're not as bad as bridges, right? Unfortunately, with bridges, they're heavy infrastructure. We cannot patch them. Whereas computing systems, we can patch them. And we should be patching them going into the future in the field with some reconfigurability, for example, and intelligence in the memory controller. Okay, I will skip these. Let me give you some final thoughts over here. Let me jump to the actually conclusion. Do we have enough time actually?
I guess you have 2 more minutes if
okay.
we reduce the Q&A session.
Okay, let me conclude then. I mean, a version of this talk is also online, so you can find it. I've skipped some interesting things, but I want to be on time. Let me conclude. So clearly memory reliability is reducing. Reliability issues open up security vulnerabilities, and these are very hard to defend against. And these are going to be critical in the field because we're going to have these systems in the field making decisions for us everywhere, including in the space. And we should be thinking about this. I think RowHammer is a prime example of such a vulnerability. As I said, it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And I believe it has a lot of implications. The bad news is this is not going to disappear. RowHammer is getting worse. It's going to get even worse. This is a fundamental technology scaling problem with DRAM, just like retention failures are. The good news is we have a lot more to do. I think we're fully aware of what's going on. We need to know more. We're developing both attacks and solutions and more understanding. And we're developing principled models, methodologies, and solutions. As I said, if you want to learn more about this, this is a survey paper that we've written that we need to update in 2023. And there are a lot more lectures over here. I'll thank people who funded this research. I'll thank my research group who have actually performed this research. If you want more information, we have a lot of lectures on this topic. And actually, specifically, we have some DRAM and RowHammer courses that make use of the infrastructure that I mentioned as RAM-related infrastructure, which is important for evaluating ideas in RowHammer and DRAM. Thank you very much. I'm happy to take any questions.
Thanks. Very informative presentation. But due to the time limit, we may only have time for one quick question. And I guess the best method to learn all the RowHammer related research is to join your lab, right?
Yeah, sure. Sure. That's a good method.
Okay.
Yeah, go ahead.
Okay. Hello, Professor Mutlu. I have a question. And now with processing memory used to be more and more frequently. So will the RowHammer have a new attack or the new protection technologies and like a new RAM blade? Yeah, thank you.
So yes, thank you. I think that's a great question. Basically, if you have processing in memory, what are the implications on RowHammer as well as processing in memory? And I think that's a good question. We've been doing some research in this area. We don't have anything fully conclusive yet, but stay tuned. So my overall feeling is that processing in memory will exacerbate these problems in the sense that you're much closer to memory and you're able to activate things much more frequently. So in that sense, it's going to get worse. But in the sense that we're going to add intelligence to the memory, we will have some solution space inside the memory by doing processing. So it will work both ways. Will there be any fundamentally new attacks? I think that remains to be seen. We don't know the answer to that, but existing attacks will get exacerbated and they will become much worse. So the interaction between processing in memory and RowHammer and in general, hardware security is certainly very interesting. And there's a lot more to do in that area for sure.
Okay, thank you.
Thanks. I guess we don't have time, but I do have one quick question. So what happens in the last year is we have DDR5. Have you ever tried the RowHammer on that?
Yeah, that's an excellent question also. So DDR5, they have introduced a RowHammer protection mechanism that's somewhat inspired by TRR. They called RFM, refresh management, which gives a little bit more options to the memory controller to protect against RowHammer. So there is some movement in a good direction, I think. We have not tried it on DDR5 chips ourselves. It also depends on this RFM solution that essentially depends on the memory controller manufacturers to use the RFM solution. So I believe solutions can be implemented to fix the RowHammer's problem securely in the memory controller using the RFM commands. No question about that. That was true even before DDR5. So in that sense, I think DDR5, we will see. The question is, those solutions are going to be expensive, basically. They will put some cost, complexity, power, and energy burden on the memory controller side. So no question about that. So if even though we haven't tried the chips themselves, once you get rid of the protection mechanisms, I believe DDR5 chips are going to be even more vulnerable, unless DRAM manufacturers have come up with a fundamentally different circuit and device mechanism that could protect against RowHammer, which I strongly believe doesn't exist at this point. Maybe 10 years down the road, yes, but today I don't believe so.
Okay, then we were expecting more results from your group about the attacking on DDR5.
Yeah, maybe other groups as well.
Yes. Let's thank our speaker again. Thanks.
Thank you very much.
Professor Mutlu.